So hello and welcome back. We were discussing out what is known as the evolutionary fuzzy inference systems, wherein we took exactly the same approach that we had taken for the artificial neural networks. We took exactly the same approach where we first modeled out the system as a standard simple genetic algorithm problem, and by this modeling we saw how we can evolve a fixed architecture fuzzy inference system. And then of course we said that fixed architecture is a very bad kind of assumption, because the major problem lies in what the architecture is. The major problem lies in how the architecture is specified, and that is when we come towards a still greater problem, the evolution of a variable architecture fuzzy inference system. And that we saw that can be divided into two parts. The first part we've already seen is that how do we evolve the how do we represent the membership functions. That is what we have already seen. Once the problem representation is over, that means it's a simple genetic algorithm problem representation, it's linear. So the entire conventional genetic algorithm I'll be able to use to solve this problem of the evolution of fuzzy inference system. So half of it we've already dealt in the previous hour of study, and today in this hour we are going to deal with the other half of the problem. And what the other half of the problem says is the rule modeling, or the individual problem representation of rules, or I can say the rules representation. Rules, again, what we said would be of multiple, there would be multiple rules in the system, R1, R2 to Rk, where the maximum rules that the system can have is L. So once I say that, I naturally know that again more or less the same things that we have dealt over and over again, is that my entire individual, I'll first need to embed the information regarding how many rules are there into the system. Now remember, it's a variable architecture fuzzy inference system, so there are variable number of rules. I do not know the number of rules in advance, but I know that there can be a maximum of L rules. So first I specify the number k, that is the number of rules. That is an information I'll have to embed inside my fuzzy inference, inside my genetic individual. This is one information that I'll have to give to the individual. And after this information has been embedded into the individual, after I have already used this information somewhere inside the genetic individual, now I need to write down all the rules inside this individual. So my complete individual would be divided up into L parts. This would store the first rule, this would store the second rule, and this would store the Lth rule. Of course, k would be always less than equal to L. The number k would always and always be less than or equal to the number L. That means it might be possible that the Lth rule, the L-1 rule, and all these rules, they are completely inactive. But again, I need to specify out something because of reasons that we have already discussed. While we were discussing in the membership functions and the associated things, we've already discussed that even though they might be inactive, they might be absent from the complete system that we have, but we'll have to specify out these things inside the individual that we have. Inside the genetic individual, we'll have to write down these things. So now it comes into how do we represent a rule as a set of numbers. That is the only problem that we have to deal with. How do we represent a rule as a set of numbers? So again, rule would contain an antecedent path and a consequent path any rule Ri will have an antecedent path and a consequent path separated by the implication operator. The antecedent path can be of format if input 1 is and input 2 is some membership function over here, and input 3 is again a membership function here. We assume that this is the general manner in which the antecedent part is written. We say that this is the general format in which an antecedent part is written. Each one of the input may additionally be supplied with that not. So it's either if input 1 is membership function 1a, or if input 1 is not membership function 1a, it can be a direct participation or an indirect participation. These membership functions can be any one of the possible membership functions. So it can be membership function to 1, it can be membership function to 2, or membership function to a2. It can be any one of these a2 membership it can be any one of these a2 participating membership functions. That is again now we have already studied that input 2 was broken down into a2 number of membership functions. So input 2 can participate with any one of these membership functions in this rule. Additionally, they can be a not over here, and additionally it may be that the input 2 does not participate in this rule. So I have input 1 is something and input 3 is something. It might be that an input does not participate at all in the rule. So based on that, when I study out any general input over here, I see that there are a variety of options that I have. If I take in any general membership function input over here, I say that there are a variety of options by which this input participates in this rule. I'm looking at how is it that an input may participate in a rule, and therefore I write down a set of options, with which this input participates in this rule, in which this membership input participates in this rule that I have written down, any rule Ri for that sake. So what do? I say that the number of options that I have for membership function 2b is that either it participates with membership function to 1, it participates with membership function to 2, it participates with membership function to 3, or it participates with membership function to a2. These are the first a2 set of options. The other options it does not participate. So this denotes that it did not participate. The other option available is that it participates with a not sign. So I'll have again a set of options that will be if input 2 is not membership function to 1, if the input 2 is not membership function to 2, if input 2 is not membership function to 3, and so on. Input 2 is not membership function to a2. These are the next set of options. So these are a2 options here, a2 options here, and 1 option here. So there are 2 a2 plus 1 options by which any input, in this case input 2, can participate out in this rule. I've done this for input 2, similarly I can do it for input 1, input 2, input 3, input 4, input 5, and I like this input n. I'll repeat this step for all the inputs. I'll trace down all the inputs that I have in my system, and I would see how is it that this input is participating in this rule. I'll see how is it that this input can participate in this rule, and because it is an evolutionary approach, the best one the best set of membership function by which this input should participate is tuned by the genetic algorithm. So all I need to do is only to embed this information inside the genetic individual. All I have to do is to make scope that this information is represented inside the genetic algorithm. The other part of it will be handled by the genetic algorithm itself, wherein it will see what is the best possible value. So now the only part left out is that how can I make the antecedent part of it as a set of integers, and that is again a very simple thing. Let me say this is that part of the individual. Let me say this is those set of genes that denote the rule Ri. Let me say this is that part that denotes the rule Ri. It will be a set of integers, of course. I'll say input 1 is participating with membership function 1a. Input 2 is participating with membership function 2b, and so on. Input n is participating with membership function nz. I'll write down all these numbers over here. They are n inputs, so the antecedent part of it will contain exactly n integers. These integers denote how is it that a membership input is that the corresponding input to which membership function it is associated. So if I have mf2b here, I know that the input 2 is participating with the membership function mf2b. In case there is a not sign in this rule, for any input I will store in a minus over here as per this set. If any input has an additional not in front of it, I'll store in the same thing, but I'll put a minus sign over here, and in case it does not participate in the rule, I'll simply write down 0 over here. I'll simply write down 0 over here. Now again, because these are set of integers, so mf2b I may not be able to write down. I cannot write down a membership function inside here. So what it is that this is written by A, this is written by B, this can be written by Z. I need to write down integers inside this and not membership functions. So I write down A, B, C till Z, where A can be any number between 1 to A1 in case there is a direct participation of the input, or it can be 0 if this input does not participate, or it can additionally be from minus A1 to 1 to minus 1 in case it participates with some membership function but with a not. So these are all the set of values from minus A1 to A1 that the first A can take. All the set of values that the first gene can take is from minus A1 to A1, and any integer denotes with what membership function it is associated to. With what membership function it is associated to. If it's the second membership function in line that it is associated to, I'll store 2. If it's the second membership function with a not sign, I'll store minus 2, and if it does not participate, I'll store 0 in this individual, and similarly I'll repeat for all the inputs. So for any rule, the first n integers, they store the information regarding the antecedents. And similar thing I can do it for the consequent. The consequent are again of very similar format. The consequents are exactly of the same format. The only thing is that I have, if output 1 is membership function 1a, if output 2 is membership function 2b, if output 3 is membership function 3c, and of course this is just a separator, it's not the AND operator. That is what we saw in the fuzzy inference system, it's just a separator. So again, if this is of the same format and they are m outputs, there are m outputs over here, I'll again use the same thing. I'll again try to write down an individual as a set of integers. I'll write down the individual as a set of integers, and that is how I would see if I am able to do that. So I have membership function 1a here, so I have a here, I have membership function 2b here, I write down b here, and similarly I write down z out over here for these m outputs. For these m outputs, I write down with what membership function any output is participating in a rule. Earlier I said that I'll write down the number of the membership function with which any input is participating in a rule. Here I write down with what number an output is participating to a rule. If it does not participate in a rule, I simply write down 0. If it does, and that is exactly as per the same norms that I took for the inputs, I write down the same norm. So if it's not participating, I write down 0. And in case it is participating with some rule, I write down a 1 over here. If in case it's participating with any of the membership function, I'll write down the corresponding number of the membership function with which it is participating, and that is how I get my consequent part. So I have represented the antecedent in my individual representation. I have represented the antecedent in my individual representation. I have represented the consequent in my individual representation. And that is what forms the complete rule. That is what forms the complete rule. And multiple rules one after the other, that is what makes the complete rule modeling of the individual. So we'll just look at what the final rule modeling is. The antecedent, they would take in a space of n for their representation. Those would be the n integers one after the other. The consequence would take in a space of n. So I require one gene for the number of rules to be specified. Any rule would require antecedent plus consequent representation. So I have a space of m plus n integers. Maximum number of rules is, let's say, L. So the complete size of the genetic individual is 1 for the specification of the number of rules plus L into M plus N. Antecedent specification plus the consequent specification. That is what the consequent bits integers I get as my complete rule modeling, as the complete modeling of the rule base that I have. And that is what completes my individual representation. The first part of it we took at the previous hour, which was the modeling of the membership function. The second part, the modeling of the rules, that is what we've taken at this hour. And both when are embedded together, that forms in a very long, a very high dimensionality but effective fuzzy inference system that is able to take its own architecture. That is what is a fuzzy system that is able to take its own architecture. So it's a variable architecture fuzzy inference system. Again, once I've done the individual representation, it's a simple linear representation. So I can use all conventional genetic operators for the evolution part. I can generate an initial population. I know the individual size. I know what are the ranges of each one of its bits, so I fill in random numbers and that gets my individual. I fill in all random numbers, that is what I get it as the individual. So I can generate initial population randomly. I can use the genetic operators of crossover, mutation, elite, sometimes some specialized operators. I can use all of them because it's a standard linear representation. And the last part of it, one part would be the stopping criterion. That is what can be conventionally written based on the fitness value, based on the performance, based on the slack time, the slack generations or anything. Sometimes maximum generations. And I have to do some kind of fitness evaluation. For the fitness evaluation, I only have a genotype that my genetic algorithm gives me. I convert it into a phenotype. The phenotype is nothing but the fuzzy inference system. I give the inputs to this fuzzy inference system. I collect the outputs. I note down the errors, or I note down the performance. And once I note down the performance, I can simply say that the fitness of any individual eye is its performance. As simple as that, as we had done in the fixed architecture fuzzy inference system. The individual performance is what the fitness is. But then again we need to consider one important thing, and that is that the number of rules and the number of membership functions need to be as limited as possible in a fuzzy inference system. That is again to control the curse of dimensionality, overfitting, overgeneralization. As we had seen in the earlier lecture on the fuzzy inference system, what the number of hidden layers and the number of neurons in hidden layers are for the artificial neural networks, the number of membership functions and the number of rules are for the fuzzy inference systems. So in order to avoid all those problems, we need to be as limited as possible in terms of the number of rules and the number of membership functions. What we had in the artificial neural network as parsimony for controlling the number of neurons, the similar concept of parsimony I'll apply here for controlling the number of rules and the number of membership functions. So parsimony means you degrade the performance by some value that is directly proportional to some penalty constant, and this penalty constant will first be applied over the number of rules. So let me say that there were k rules, so it will first be applied over the number of rules, and it will then be applied over the number of membership functions. So number of membership functions, summation ai plus summation bi, I from 1 to m here and I from 1 to n here. And alpha and beta are both penalty constant. This is the penalty constant for the number of rules, this is the penalty constant for the number of membership functions. So these are the two penalty constants that we have used, and this is what I have applied it as a parsimony, where I am trying to apply some penalty for oversized fuzzy inference system. I am applying some kind of penalty for fuzzy inference systems that take in oversize. Initially, when the size is very low, addition of some membership functions, some rules will result in a great boost. So the performance will outpower the growth in size. But when the networks are enough advanced, a little growth in the number of membership function or the number of rules will result in hardly any performance. That is where the penalty will outperform the performance. The penalty will easily outperform what the actual performance of the system is. And that is how oversized network will be disregarded because of this parsimony, and because of the same properties that we have because of parsimony, the network will not, or the fuzzy inference system in this case, not a neural network, a fuzzy inference system will not go into regions of overtraining. So by this I complete all the steps involved in evolution of a fuzzy inference system. Of course, I took in another third example in the neural network where I said that there was some kind of incremental evolution of neural networks. The same thing can be applied to fuzzy inference systems as well, where the number of membership functions increase along with time by some deterministic adaptation, where the number of rules they increase along with time. And of course, there is a specialized kind of genetic operator used, there is specialized kind of operators that we make, there is a specialized kind of evolution that we carry out. The same phenotype representation may be used, the operators may be adapted. I did not repeat the same discussion out for now. There is a very small topic that I will be covering in before we start off with the next set of hybrid systems. Before we start off with the next class of hybrid systems altogether, there is a last thing that I would be taking, and that is evolution of a learning rule. Now I am again into neural network with some kind of genetic algorithms. So I'm not into fuzzy inference system as of now. I'm into some kind of neural network with genetic algorithms. What I am discussing is that consider the multi-layer perceptron. I apply an algorithm that is known as a back propagation algorithm in order to carry out the learning of an artificial neural network. I use a back propagation algorithm. The back propagation algorithm is usually based on some kind of gradient descent approach, wherein I calculate the gradient, try to compute where the minima is, and then go out over here. That is what I do. I write down a set of equations where I calculate my delta wij for any hidden layer, and for any connection between neuron I to neuron j, I calculate delta wij based on all the set of equations that I had written, and I simply say that wij at time t plus 1 is nothing plus wij at time t plus delta wij. That is what we learned in the artificial neural network, where the old weight is, where the new weight is the old weight plus the change in weight. But the problem lies in the fact that how good this equation is. The gradient descent approaches, the back propagation is always based on some assumptions. It's always based on some assumptions. So are these assumptions holding true? When I have a general highly dimensional input space, or let me say in this case not an input space because it's an optimization problem, a weight space. In any general highly dimensional weight space that I have, where the error is plotted against all the weights and the biases, is this equation holding good? Is this equation performing best? Is it able to recover from all local minima, converge to some global minima, and all these things? Is it able to carry out good and effective convergence? Is it able to give me a very reduced error? Is it able to give me a very high performance? That is a debatable question. So can I apply some kind of genetic algorithm in order to optimize this equation? So can I apply some kind of genetic algorithm to optimize this equation? Because we know the modeling that the backpropagation algorithm does, it may not be perfect. The modeling that the backpropagation does, the kind of equation that it uses, it might not be perfect. So can we evolve this perfect equation? And now the question is only that in place of this equation being written by the backpropagation algorithm derivations, can it be written by a genetic algorithm? So this problem specific equation, now remember backpropagation algorithm is a generalized equation, we are writing down a problem specific equation as per the demands of the fitness landscape or the weight space. Can I write down a perfect equation for this landscape over here? I write down this equation using the genetic algorithm. So let me say that for now delta wij, what all does this function it depend upon? What all is that this function depends upon? That we need to find out. If it's some function, it will take in some inputs, and based on these inputs, it will change me what the change in weight is. So now I find out what are the factors that are affecting the change in weight. I need to find out the factors that are affecting the change in weight, or the inputs that I get to this function, it will give me the change in weight. These factors that affect the change in weight, or these inputs that affect the change in weight, I take it directly from the backpropagation algorithm. So whatever were the inputs to the backpropagation algorithm that gave me the change in weight, I use exactly the same parameters, I use exactly the same inputs to this function, again motivated by the backpropagation algorithm. So all I've done is that I'm trying to optimize the backpropagation equation. I'm trying to optimize the backpropagation equation. I'm not trying to change in the inputs. I'm trying to change in the other parameters and the other relationship that it has. So I use exactly the same inputs that my backpropagation algorithm has, which again repeating the same lecture, which again repeating what we studied earlier was something known as the previous weight. it had elements of previous weight being added to the equation where we were taking the delta and all. From any neuron I to any neuron j, it considered what is the output that is produces out there. It review what is the kind of activation that it produces. So it's an output. It's some kind of output that was produced out in that system. It kind of used that output as a measure of how much that weight should change. It uses kind of output that was a measure of how much change it should make. It again used some kind of activation that was produced by this neuron. And this activation was again a set of information to me to how much exactly this weight should change. And based on that, I calculated how much, what should be my equation based on the backpropagation algorithm. So I used exactly the same inputs out here that were used in case of a backpropagation algorithm. I have exactly the same inputs out over here. Now again the thing is I had to give a linear representation, which I'll again not be able to do out in this case. So I assume that this equation be of the format k1wij plus k2oj plus k3tj. I assume that this equation is of this format. So I've taken up the change in weight to be directly proportional to the parameter to these inputs and plus a combination of them. Now I could take up 3 combinations of them, I could take in 4 combinations of them and the higher order, but I always avoid the higher orders. It will make my landscape it will make my equation very complex. It will make the individual very complex, so I'll avoid all the higher order. I'll only take the order of 2 where their direct relationship has been taken and their combination has been taken. I've taken them directly, alone and in combination with 1. So all I need to optimize is K0, K1, K2, K3, so I make it a simple individual. I write down all K0, K1, K2, K3 up to whatever the final number be Kn as a genetic individual. Now any genetic individual now contains information to what the learning rule is. It contains that exact equation that was in earlier case by backpropagation algorithm. So I can generate an initial population. I can use the conventional genetic operators, and when I try to find out fitness, I can simply make my neural network learn by this equation that is generated from the genotype. This is the genotype, this is the phenotype. I can make my algorithm generate this equation and learn by this equation, and whatever error it gives is a measure of the cost value or the reciprocal of the fitness value. So using this I can find out some kind of equation that has been genetically optimized as per the problem requirement. So if there are any limitations of the backpropagation algorithm, we try to remove them using the genetic algorithms. So this is what is known as the evolution of a learning rule. So we have seen into the set of hybrid computing 2 exciting systems. One dealt with the application of genetic algorithm to the neural network, which was the evolutionary neural network. The other dealt with the application of genetic algorithms again into the problem of fuzzy inference system. Those were the evolutionary fuzzy inference systems. So we are done with these 2 systems. Now we take in the application of multiple neural networks for problem solving. We take in application of how multiple neural networks can be used for the task of problem solving, and the first thing that we take in this are the modular neural networks. We will study what the general class of the modular neural network is all about, and then we will of course try to make in some specialized neural networks that are used for problem solving. Now, what do we mean by, of course it's a neural network, so it will be the same neural network architecture, but one additional word that I have introduced is the word modular. Now again, if we go into the principles of software engineering, modularity is something that we consider in every kind of software. We make in different classes, all the different classes perform some kind of task. All the different classes, they perform some different kind, they use their own tools and means for problem solving. And what I am supposed to do is to call one class from the other, make objects of the second class from the third, and all this integrated system that solves the purpose for me. That is the whole entire complex software that a user gets all its functionalities from. So a user probably clicks on some button out there as a nice GUI screen, and it's all a modular architecture of the software that lies after it. So is it that we can introduce the concept of modularity inside our neural networks. Now, why do we need modularity when it comes to the neural networks? Why is it that a single neural network cannot solve the problem? That again goes for the fact that the problems that we normally deal with in real life, they are fairly complex in nature. All these problems are fairly complex in nature. If they are fairly complex in nature, a single neural network might not be able to solve them. We might never have that a single neural network I employ and that solves complete task. It may not be possible for a single neural network to solve the problem. In order to solve the problem, what I'll additionally do, I'll increase the number of hidden layers, I'll increase the number of neurons in the hidden layers, and then I'll see that can my neural network solve the problem now? Because in a limited size it has limited functionalities and it could not assume a complex shape, and because it could not assume a complex shape, it could not solve that complex problem. So I say by increasing the number of hidden layers, neurons, can I now solve the problem? And it is well known that now the problem that comes is curse of dimensionality. And curse of dimensionality states that now you will require excessive training time, you will require excessive training data, the training may be suboptimal, the training may not be possible, wrong training might happen where only the regions where the training data is in, it might solve nicely. So again, this option has been ruled out. Now the basic problem lies is that I cannot solve a complex problem by a simple neural network because of its simplicity, and I cannot solve it by a complex neural network because of the curse of dimensionality. So how is it that I am able to solve complex problems in reality? So the complexity of the problem is one of the essential problems. The other problem lies in the fact that when a single neural network is told that you learn this database, you solve this problem, you assume in shapes for this problem, it might be computationally very expensive for it to do so. It might not be computationally possible to have so much of computation inside it so that this problem is solved. And since we do have limited computation, we would like to solve the problem, the complex problem anyways. That is when we would like to think over some means by which the same problem can be solved using some computationally inexpensive technique. Now as a result, what do I do is that if I can completely not solve a complex problem using a single neural network, if I am completely unable to solve this problem using a single neural network, I see that can I study the problem and introduce some kind of modularity inside the problem? Can I introduce in some kind of modularity inside the problem so that the simple problem or the complex problem is divided into a set of smaller problems? Can I analyze the problem manually or using a computationally intelligent technique or using some automated technique? Can I analyze a complex problem and break it down into set of smaller problems which are all nothing but modules, which are nothing but independent modules. Now this task is exactly the same that normally you are given a task of making in a software, and you break it down into a set of independent modules, into a set of smaller modules that together make in the complete software that you are looking for. The various components, they are connected, that we draw using a class diagram in a very complex manner. Similarly here, the smaller problems may be connected in a very complex manner, or they may be connected in a very simple problem. Depends upon how you are introducing modularity into your system. It depends upon how is it that you are trying to modularize the complex problem that you have been able to give, that you are given. Based on that, you may break it up into a set of smaller problems, and the architecture is again dependent on how is it that this problem is broken, whether it's broken by a human or it's broken by an automated technique. But the end result is that now I have got smaller problems, sometimes interrelated problems, and of course I can use in simple ANNs, smaller ANNs to solve these simpler problems. I can always use some kind of smaller ANNs to solve these problems, and hence when this problem is solved, then these are all interrelated. That means my bigger problem is solved. When each one of these smaller problems is solved, I know that my bigger problem can be solved. So what this again brings forth towards our discussion is something that we normally study in algorithm, that is known as the solution of divide and conquer. In the algorithms domain, we usually deal up with so many problems where we say that you are given a problem, you divide it into a set of smaller problems, and then you solve them up. So what the principle of divide and conquer says is that I am given a problem, I divide it into a set of sub-problems, there was a problem that I was given. I was given some kind of problem. I have divided it into a set of similar problems, similar sub-problems, whose complexity, whose size is smaller than the main problem. I solve each one of these problems. So if there was a problem here, I solve all these problems. Once I solve these problems, I have got the individual results. Then is when I combine these problems and get my solution to the main problem. So this is what is the main problem. This is what is the solution to main problem. This is what is the solution to sub-problem. And these are what the similar sub-problems are. The division of problem to sub-problem is known as a divide phase, and the integration of the solution to various sub-problems to form the main solution is known as the conquer phase. So there is a divide phase and there is a conquer phase. The divide phase is when I divide my main problem into a set of similar sub-problems. That is what is the divide phase. The conquer phase is where I integrate the various solutions to sub-problems and get my final result. That is what the conquer phase is. Now since these are similar problems, these are smaller problems, all these can be solved while the main problem could not have been solved. The smaller problems may be solved when the bigger problem cannot be solved. And once the smaller problems can be solved, I can integrate all these smaller problems to get my final result. That is again divide and conquer, the main principle that we use behind the modular neural networks, or sometimes known as the MNNs. That is what is the main concept that we use behind the MNNs, where the divide and conquer principle is used. Of course, these smaller subproblems may even be large, so these smaller can be broken down into still smaller problems, The still smaller can be broken down into still smaller problems until and unless we get a unit problem that can be conventionally solved. We get such a simple problem that can be conventionally solved. Then is when we stop dividing. And similarly for integration. Once I get in a problem that can be conventionally solved, I integrate all the similar problems. I get a result to a bigger problem. I integrate all the solution of bigger problems. I get in a solution to a still bigger problem until I get the final solution for my main complex problem. That is what the conquer phase is all about. So that there is a divide phase and there is a conquer phase, the principle behind the modular neural networks. Again, as it is said, that is there any motivation from the nature and biologically inspired world? Is there any motivation that we can take up from there? Now again consider what this is all about. That whenever the brain does kind of processing, we know there is a part of brain that is for the eyesight, there is another part of brain that is for the hearing, there is another part of the brain that is for thinking. So the brain can be easily divided into some kind of modules with the task of each and every module being rightly defined. So some way the brain is nicely modularized. Even though it is a very complex connection of 10 raised to power 11 neurons with some 10 raised to power 22 connections, still the modular architecture is very well there, where every part of the brain does some specialized task. So there is some kind of modularity there. Again, there is some kind of hierarchy processing there, as we had seen, that if it's an eyesight, the first few layers would only identify the lines and the dots. The next few layers would identify some complex curves. The still higher layers might identify the objects. The still higher ones might identify complex objects. So there is some kind of modularity that already exists in the brain, and that is what we are trying to implement out here in case of modular neural networks. That is what we are basically trying to do. Again, we move forward to the next. In the same class of modular neural network, we move on to what is normally known as the hierarchical neural networks, where I use in not one but multiple neural networks for problem solving. So the complete architecture would be something like this can be the ANN1, this can be the neural network 2, this can be another neural network 3, this can be a neural network 4, this can be a neural network 5, this can be a neural network 6, and so on. There are various multiple neural network connected in different mechanisms. This can be a neural network, or sometimes it can just be an integrator which does some kind of basic computation of integration of the various results as per the problem requirements, as per the modeling scenario, as per whatever this has been implemented as. Now when I say it's a neural network, it is nothing but what takes in inputs. So there are some input neurons over here, there is a complex architecture of hidden layer neurons over here, there are some output neurons out over here. This is what gets into here and here. Again, this has a set of inputs that it gets a complex architecture out over here. Some output neurons out over here, they go out over here, and that's how the entire architecture is. So each and everything that I draw it out as a box here is nothing but an artificial neural network. Since it is an artificial neural network, each one of these artificial neural networks has its own training database, it has its own training outputs, it has its own model. Not necessarily that they are all multi-layer perceptron as known here. Some of them can be radal-based functions, some of them can be self-organizing maps, some of them can be recurrent neural networks. Any architecture would do. They all can be trained in parallel. They are all independent, so they all can be trained in parallel. They are all nothing but modules. And if they are modules, they can be all trained out there in parallel. And what I get it as the complete architecture. What I get as a complete architecture is what is known as a hierarchy neural network. Another time, it's of course under the general class of modular neural networks, where I draw these as the separate modules. Each one of these is nothing but a module in itself. So once this architecture is made, I can again state that this is again from some kind of inspiration that we take up from the brain, where there are specialized networks performing some specialized tasks. The complete complex task is broken down into some simpler subtasks. Each subtask is handled by some different neural networks. Each subtask is produced by some different network. Every network knows what kind of inputs it gets and what kind of outputs it gets. Sometimes it is one processing followed by the other processing. So there is a one task, what becomes the output of this neural network becomes the input of this neural network, where some processing is done by this neural network and the corresponding processing is done by this neural network. Sometimes the problems they identify which neural network is to be invoked depending upon the problem type, depending upon the type of information to be processed. Sometimes all these neural networks are made invoked, all of them are made active, and each one of them knows what it is supposed to be do for the common set of inputs that they are given. They all know that what is the processing that they need to be performed and how will it benefit the other networks in the modular architecture. So that is what the complete modeling is all about. Again, the modeling is application specific. It's all specific to what kind of problems you are solving and how is it that you are trying to solve the problem. How is it that you have discussed, how is it that you have modeled the information processing to take place. So this is what is the general class of the hierarchical neural networks. Now before we, of course, I'll take in the modular neural network and I'll take in a specific architecture where I use the same problems of maybe functional prediction, maybe classification, and at ground level we'll see as to how is it that we try to introduce modularity and solve these problems. But before taking out any specific example, let me give again a very general notion of what is known as the ensembles. The modular neural network was some kind of hybridization of neural network with themselves, where we see that what cannot be done with a single neural network can be done with multiple of them. Ensembles are exactly the same thing, where I use the same concept that what cannot be done with one neural network, let's try to do with multiple of them. The only difference is that modular neural network had their motivation from modularity to solve complex problems what would have otherwise not been problem. Ensembles is nothing but solving problems redundantly. It's all about problem solving with some redundancy. Now, what is it that it's redundancy? Well, how is it that I have some kind of redundancy, and why do I solve this problem redundantly? That is what needs to be understood. Now, I have been given some kind of problem in hand. I have been given some kind of problem in hand, and I have been asked to solve this problem. Now, the first question that comes is that which model of neural network should I use? A radial basis, self-organizing map, probabilistic neural network, recurrent neural network. What is the problem? What is the model that I use for solving this kind of problem? The other issue comes is that what kind of parameters that we use for solving this problem, which is of course another complex task. We saw that it was so complex that we needed some kind of evolutionary computing for this to be done. And towards the end, all I get is a kind of model along with parameters that by some computationally experiment technique, by some manual work, by some of hard work, but a lot of experimentation was found to be optimal among the set of available options. But is it that what the final model that I get is optimal in nature, in totality? Can I try to get in some extra benefits by any other means if I use multiple neural networks to solve the problem. That is what this technique is all about. It states that there is again a problem. I solve this problem by a variety of methods. I solve exactly the same problem by a variety of methods. Now in modularity there was some kind of division in computation happening. There was some kind of division in computation happening, that what is performed by one neural network, the same processing is not performed by the other neural network. The other neural network performs some different kind of computation. The third neural network does different, looks at it from a different aspect. It performs computation at any third perspective. Here, all the neural networks are given the same problem. If it's a simple problem, all of them are given simple problem. If it's a complex problem, all of them are given the same complex problem. So each and neural network has got in the same set of inputs, the same set of problem to solve. That's why I say it's redundant. What this person, expert is doing, what this neural network is doing, is being performed by, the same task is being performed by this neural network, the same task is being performed by this neural network, and exactly the same task is being performed by the last neural network. All the neural networks are performing the same task. And if all the neural networks are performing the same task, we look at it into what the advantage is. Now whenever I use any intelligent technique, finally I get a model with parameters. But this model always has got some limitations. There are some limitations that it needs to follow. There are some limitations that are intrinsic into this model. No matter what optimization I apply, because these are intrinsic into the model, I cannot remove those limitations. So as a result, what happens that the final system that I have using a singly studied model also has those limitations, and hence the optimality is low, or I say that the final system that I got is suboptimal because of those limitations that are of modeling that are already intrinsic into the model. Now again, numerous examples that can be given. If I solve, if I take in a neural network that has less number of neurons, it can only have some kind of underfit curve. It cannot take in an ideal fit or an overfit. Of course, I do not know what an ideal fit is. If I take more neurons, then there would be some kind of overfitting. And I may not be able to decide using any technique whether I am going for a neural network with higher number of neurons or a lower number of neurons. And hence, the problem lies in that both of them are not useful for me. Even the ideal structure that I get, even if I try to find out the ideal structure, it may either give me an underfit or it may give me an overfit. So there might be no combination possible in which I get an ideal fit. So this might be one of the examples where increasing one neuron I am getting an overfit and decreasing it I am getting an underfit, and that is a problem intrinsic into the backpropagation algorithm. Again, if in some regions the fitness landscape is very delicate, both of them would be useless. I have to use some kind of modeling scenario which is different for some part of the input space, different for the other part. So all these problems are intrinsic into the model, and as a result I cannot make it a very flexible model using a single model. I cannot get complete flexibility because of the problems intrinsic into this model that I am using. So what do? I redundantly solve the problem by multiple networks, and I see if I can integrate all these results and get the final result, get the final output O. And as a result of this, what happens? The advantages of one neural network are overcome by the disadvantages of one neural network are overcome by the advantages of the other neural network. The advantages of one model overcomes the disadvantages of other model, and that is why the complete problem being redundantly solved. All these cooperate with each other, all these help each other to solve their limitations and maximize the advantages, using this integration. So this is what is known as the task of integration. Now the entire concept of modular neural network and this in simples, it's also known by the name of committee of experts, mixture of experts, and multiple names that are given out to them. We'll be seeing into a little depth of how this is carried out, how that is carried out with specific examples. That will be what would be the agenda for the next hour of study.